You are in a dark control room, staring at a screen while a signal crawls toward Earth from farther away than almost anything the human mind can picture. Voyager 1 is a small, aging machine built in the 1970s, no bigger than a compact car, and still drifting where no craft was ever meant to survive. What it found near the edge of the sun's great bubble did not look like the clean border scientists expected, and the farther its whisper traveled, the more that border seemed to move, bend, and refuse a simple answer. If you want more deep space stories told in a way that makes the giant stuff feel close enough to hold, stay with this channel and subscribe. It is easy to imagine the end of the solar system as a hard line, a bright fence, a last marker. One side is home, and the other side is the black unknown. But space does not like neat edges. Space likes foggy borders, slow changes, and surprises that only show up after years of waiting. Voyager 1 keeps forcing that lesson on us. Its pictures are long gone. Its cameras were shut off decades ago. It no longer sends us grand views of planets rising over darkness. What it sends now is thinner than that. Numbers, tiny shifts, faint waves. A whisper from a place where even sunlight feels less like a beam and more like a memory. And yet those whispers have redrawn one of the oldest maps we carry in our heads. Because the story of Voyager reaching the edge of the solar system is not really the story of a machine arriving at a border. It is the story of finding out that the border itself is alive, unsettled, and stranger than the textbooks promised. To see why this matters, we need to step back. Most people picture the edge of the solar system as a simple outer wall, and once a spacecraft crosses it, the story is basically over. Outside is just empty interstellar space, cold and silent, with the sun's influence left behind like a town in the rearview mirror. That is the version that sounds clean, and for a long time it felt close enough to true. Voyager began as something much easier to understand. It was not built to become a ghostly border scout for half a century. It was built for a grand tour of the giant planets. Voyager 2 launched in August 1977. Voyager 1 followed in September, just 16 days later. They left Earth carrying late 1970s electronics, long booms, dish antennas, and power systems fed by the slow decay of plutonium. At first, their story was loud. Jupiter came in 1979 with its storms, its moons, and its crushing scale. Saturn followed in 1980 with rings that looked almost soft from a distance, even though they were made of ice and rock. Voyager 2 kept going after that, racing on to Uranus in 1986 and Neptune in 1989. Those flybys alone would have made the mission legendary, but the part that made Voyager immortal began after the big postcards stopped. In 1989, the mission became the Voyager Interstellar mission. The goal changed from looking at planets to studying the outer skin of the sun's influence. That skin is the heliosphere, the vast bubble made by the solar wind, which is a stream of charged particles blowing out from the sun in every direction. That bubble sounds smooth when you say it fast. It is not. It swells and shifts. It presses against the thin gas between the stars. It is shaped by magnetic fields you cannot see and particles you cannot feel. Imagine breathing into freezing air and watching your breath push outward, fade, and mix with the cold around it. Now make that breath bigger than the orbit of Pluto. By the time the Voyagers entered that outer region, they were already doing something eerie. They were heading into darkness so deep that the sun no longer looked like a warm center of life. It looked like one bright star among many. The spacecraft themselves kept going in silence, warmed by their own fading power, and speaking in radio signals so weak that, as NASA later put it, Voyager 1 was transmitting with about the power of a refrigerator light bulb. Scientists had a general picture of what should happen next. First came the termination shock, where the solar wind should slam into resistance from interstellar space and slow down hard. Voyager 1 crossed that region in December 2004 at about 94 astronomical units, with 1 astronomical unit meaning the average distance between Earth and the Sun. Voyager 2 crossed it in August 2007 at about 84 astronomical units. After that, both spacecraft entered the heliosheath, the outer layer of the Sun's bubble. This was supposed to be the setup to a clean ending. The wind would weaken, the Sun's hold would thin out. A final boundary called the heliopause would mark the edge, and beyond that would be interstellar space. The map had a tidy feel to it. Inside the bubble, solar space. Outside the bubble, star space. It sounded almost comforting. Then the measurements started to misbehave. In a 2005 report highlighted by NASA's Jet Propulsion Laboratory, Ed Stone of Caltech described 3 surprises from Voyager 1 near the solar system's edge. The solar wind beyond the termination shock was expected to keep moving outward, just slower. Instead, it became much weaker than expected, and at times seemed to flow back inward toward the sun. The magnetic field also acted strangely. Scientists expected its direction changes to keep sweeping past in a steady rhythm. Instead, that rhythm stretched out. JPL described the field like giant zebra stripes that once passed every 13 days, but then took more than 100 days to switch. The edge was not acting like a crisp line. It was acting like a place where motion itself had become confused. The biggest surprise was the one that did not happen. Scientists expected certain cosmic ray particles to peak right at the shock. That was the idea. That was the nice, clean prediction. But Voyager 1 did not find the maximum there. The intensity kept rising farther out, which meant the source of those particles was somewhere deeper in the mystery, not at the spot where many thought the story would peak. Still, even with those warning signs, the old picture held. There would be an edge. Voyager would cross it. The border might be messy, but a border is still a border. That assumption sat quietly inside almost every retelling of the mission. The farther Voyager went, the more people imagined the finish line ahead, waiting like a final gate in the dark. Then the gate stopped looking like a gate. The farther Voyager pushed, the less the edge behaved like an ending, and the more it behaved like a conversation between 2 oceans. Write the exact moment this picture started to crack for you in the comments. That helps us see which hidden turn deserves the next deep space story. What we have just taken for granted turns out to be only the outer shell of a much larger story, and the next stretch is where Voyager stopped confirming the map and started rewriting it. In August 2012, Voyager 1 hit a change that looked dramatic enough to be the answer. The count of particles from inside the heliosphere dropped. Cosmic rays from outside surged. That was the kind of switch scientists had waited years to see. The old expectation was simple. When the local solar particles fall and the galactic ones rise, you have crossed into interstellar space. But one crucial instrument on Voyager 1 had failed decades earlier, so the team still lacked the clean plasma reading that would make the case final. That missing tool changed everything. The plasma science instrument on Voyager 1 had stopped working back in 1980, so the spacecraft had reached the most important border of its life with one eye closed. It was like hearing a door slam in another room and knowing something had changed, but not being able to see who walked in. The data felt convincing, but not complete. Then the sun helped by accident. In March 2012, a coronal mass ejection, a huge burst of solar material and magnetic force, blasted outward. 13 months later, in April 2013, that wave finally reached Voyager 1. Don Gurnett and the plasma wave team at the University of Iowa listened as the plasma around the craft began to vibrate. In a science paper announced by JPL in September 2013, those vibrations revealed something stunning. Scientists expected a denser plasma outside the heliosphere. What they found was plasma more than 40 times denser than what Voyager 1 had been measuring in the outer heliosphere. The surprise was not just that it was denser. It was how clearly the numbers shouted that Voyager had entered a new region. It was like stepping from a dry room into water and realizing the whole space around you has changed its weight. That gave the team a date they now generally accept: August 25, 2012. Ed Stone said, "Yes, we are there." Humanity had its first machine in interstellar space. That alone would have been enough for history, but the next twist came fast. Even after this crossing, the data did not look like a total break from the sun. The environment outside still seemed disturbed, touched, shaped by the bubble Voyager had supposedly left behind. Nathan Schwadron of the University of New Hampshire and colleagues looked again at Voyager 1's magnetic field data in work published in Astrophysical Journal Letters. The expectation had been that once outside, the local interstellar magnetic field would point in a distinctly different direction. Instead, Voyager found a field more than 40 degrees off from what other spacecraft and models had suggested for pristine interstellar space. The clean handoff did not happen. Schwadron's team argued that Voyager 1 was still in a distorted region just outside the heliopause, where the solar wind was still bending the field. If the magnetic field was like a rubber band around a beach ball, as he put it, the band was being deflected around the edge. In other words, Voyager had crossed the border, but the border kept reaching back. The outside was not fully outside yet. That alone would have been enough to make scientists uneasy. Then Voyager 2 arrived with fresh instruments and a second angle. On November 5, 2018, Voyager 2 crossed the heliopause. Unlike its twin, it still had a working plasma science instrument. In 2019, 5 papers in Nature Astronomy laid out what it found. Scientists expected the second crossing to confirm the first and make the picture cleaner. It did confirm some things. It also made the edge even stranger. Voyager 2 showed that interstellar plasma just beyond the heliosphere really was denser than the plasma inside, just as expected. It also showed that it was colder than the plasma inside the heliosphere, again as expected. But then came the twist. The plasma outside was slightly warmer than scientists had predicted, and there was a slight increase in plasma density just before the crossing. That suggested compression on both sides of the boundary. The expected picture was a neat handoff between one region and another. The actual picture looked more like 2 weather fronts piling into each other. Not a wall, not a blank line. More like a tide zone where foam piles up and the water never sits still. JPL said scientists still did not fully understand what was causing the compression on either side, and that uncertainty matters. It tells us the edge is not just unknown to the public, it is still unsettled among experts. Voyager 2 also exposed another surprise. If the heliosphere was a ship moving through interstellar space, the hull was expected to be protective. Maybe not perfect, but fairly firm. Instead, one of Voyager's particle instruments showed that some particles from inside the heliosphere were leaking through the boundary into interstellar space. The edge was not sealed, it was porous. And this is where the story gets almost unfairly strange. Voyager 1 had crossed closer to the front of the heliosphere, the nose of the bubble as it moves through space. Voyager 2 crossed closer to the side, or flank. The expectation was that the same border would behave broadly the same way. What Voyager 2 suggested was that the flank might be more porous than the front. So the edge of the solar system was not one thing. It had local behavior, like a coastline with cliffs in one place and marshland in another. Then came the magnetic field result. Outside the heliopause, scientists expected the magnetic field direction to change in a way that made the inside and outside clearly distinct. Voyager 1 had already hinted at something odd, but with only one crossing, it could have been a fluke. Voyager 2 confirmed the same basic pattern. The magnetic field just beyond the heliopause was parallel to the field inside. The border separated 2 regions, but their magnetic directions seemed to line up. That is, one of those findings that sounds small until you sit with it. The neat expectation was a corner. The real finding was more like a seam. Imagine opening a jacket and discovering the inner lining runs in the same direction as the fabric outside. The cut is real, but the pattern carries through. The sun's bubble did not end in the dramatic magnetic twist many imagined. And the implications ran backward toward home. According to JPL's summary of the 2019 Voyager 2 results, Voyager 1 had already shown that the heliosphere protects Earth and the other planets from more than 70% of cosmic radiation. That means this invisible bubble is not just a space fact. It is part of the shield that helped make our neighborhood livable. So when Voyager found leaks, compression, and odd magnetic alignment at the edge, it was not just sketching a border. It was testing the quality of the walls around our house. Years later, another whisper arrived from farther out. In May 2021, Cornell reported that Stella Koch-Oker, working with James Cordes, Shami Chatterjee, Donald Gurnett, William Kurth, and others, had found a faint, persistent hum in Voyager 1 data, published in Nature Astronomy. Scientists expected plasma wave disturbances after big solar outbursts. What they found between those outbursts was a steady, monotone emission from the interstellar medium itself. The expectation was thunder, followed by silence. The actual finding was thunder, followed by gentle rain that never fully stopped. Oker called it a faint, persistent hum. Cordes compared the interstellar medium to quiet rain, with solar outbursts like lightning bursts in a storm. That is a beautiful image, but it is also a serious scientific shift. It means interstellar space near Voyager is not a dead emptiness waiting passively for events. It has its own texture, its own ongoing low-level voice. About 2/3 of the way into this story, honesty matters more than drama. Scientists still do not fully agree on the exact shape of the heliosphere or all the reasons its boundary behaves this way. The compression on either side of the heliopause is not fully explained. The precise way local interstellar magnetic fields wrap and distort around the bubble is still being worked out. That uncertainty is not weakness. It is the sound of real discovery still happening. And that is what makes Voyager's findings so hard to file away. Every time we think we have reached the stable summary, the data pushes back. The edge is not a simple shell. The outside is not fully detached from the inside. The border leaks. The magnetic fields align in ways that feel too tidy where they should be messy, then act messy where we hoped they would be tidy. Even the emptiness hums. There was another reminder that this mission is still alive in the least glamorous way possible. In November 2023, Voyager 1 suddenly stopped sending readable science and engineering data. JPL later described it as the start of a months-long effort to diagnose a problem on a spacecraft billions of miles away, built on systems designed in the 1970s. Imagine trying to repair a typewriter with a flashlight, except the typewriter is beyond the planets, and every exchange takes nearly a day. That is the scale of patience this mission demands. So when people say Voyager reached the edge of the solar system, the line is true in one sense and incomplete in a deeper one. Yes, the spacecraft crossed the heliopause. Yes, it entered interstellar space. But what it found there was not a clean after-picture. It found a border still carrying the fingerprints of the sun. It found a place where categories blur, where one environment presses into another, and where the old map keeps fraying along the fold. And here is where this stops being about one machine and begins being about us. If Voyager's reveal is right, then the way we picture safety, distance, and even home in space has to become less rigid and more alive. Pass this video to one older skeptic who thinks space stories are only about faraway rocks and big numbers. That share can start a real conversation about the hidden shield wrapped around every day of life on Earth. Because once the border stops being a line and starts being a living zone, the question changes. We are no longer asking only where the solar system ends. We are asking how our star negotiates with the galaxy, how good our shield really is, and what kind of neighborhood our descendants will move through when they finally send machines, or people, farther than Voyager ever could. That shift matters right here at home. On Earth, we trust boundaries all the time. A front door keeps weather out. A roof turns rain aside. A windshield lets light in while blocking the wind. The heliosphere may be doing something like that for the whole solar system, reducing the cosmic radiation that reaches the planets. If that shield is lumpy, shifting, and partly leaky, then the future of deep space travel is not just about engines. It is about weather at the edge. It also changes how we think about exploration itself. A lot of us grow up with the idea that discovery means finding the place where the blank on the map ends. But Voyager shows something harder and more honest. Sometimes discovery begins right after the line you were waiting for. You arrive at the border and learn the border was only the introduction. The real mystery is the zone around it. That is why new missions that study the heliosphere matter so much. Voyager gave us direct samples from two lonely points. Missions like IBEX, which spotted a mysterious ribbon in energetic neutral atoms, and later efforts built to map the heliosphere in broader ways, are trying to turn those isolated whispers into a fuller picture. Voyager gave us pinholes through a curtain. The next generation is trying to show the curtain's shape. The more we learn, the more the human stakes sharpen. A future crew heading far beyond Mars will not travel through abstract textbook space. They will move through particle storms, magnetic structures, and changing radiation conditions set partly by the strength and shape of the sun's outer bubble. What Voyager found is not only a space mystery, it is early fieldwork for routes our species may one day try to cross. And Voyager itself keeps teaching even as it fades. In February 2025, JPL announced that engineers shut down the cosmic ray subsystem on Voyager 1 to save power. In March 2025, Voyager 2's low-energy charged particle instrument was shut down as part of the same effort. NASA said both spacecraft lose about 4 watts of power each year. That is not much in daily life. Out there, it is the slow ticking away of what remains. Those shutoffs are painful because each instrument is a sense, and every lost sense narrows the story. But they are also strategic. Suzanne Dodd, Voyager project manager at JPL, said if engineers did not turn instruments off when needed, the spacecraft might have only a few more months of power before end of mission. By managing those losses, the team believes at least one science instrument on each spacecraft could keep working into the 2030s, though unforeseen trouble could end that earlier. The distances alone feel almost rude to human intuition. JPL said in 2025 that Voyager 1 was more than 15 billion miles away, and the one-way radio travel time from Earth to Voyager 1 was over 23 hours. Voyager 2's signal took about 19 hours. A command leaves Earth, crosses almost a full day of emptiness, reaches a machine built before most modern home computers existed, and then another long wait begins. Space exploration at this range is less like steering and more like sending bottled messages across a moving sea. Then, on April 17, 2026, engineers shut down another Voyager 1 instrument, the Low Energy Charged Particles Experiment, or LECP. NASA's mission status information updated that same day showed Voyager 1 still operating its magnetometer and plasma wave subsystem. Voyager 2 still had its magnetometer and plasma wave subsystem on as well, while other instruments had been turned off either to save power or because their performance had degraded. The spacecraft were no longer working with a full toolbox. They were surviving on the tools that still mattered most. And yet the future horizon kept moving forward. NASA's current mission page says Voyager 1 is approaching 1 light day from Earth, meaning the distance light travels in 24 hours. The date NASA gives is Wednesday, November 18, 2026, at 2:16:07 a.m. Pacific Time. At that moment, Voyager 1 will be 16,094,799,096 miles from Earth, or 25,902,068,356 kilometers. That number is so large it almost stops meaning anything, which is why the phrase "one light day" hits harder. It means tomorrow's sunlight could never catch today's Voyager signal in time. There is something deeply human in that. In your own life, a day is a school day, a work shift, a family visit, a long drive, a night of bad sleep, a birthday dinner, a silence after an argument. For Voyager, a day becomes distance. A full day of light becomes the gap between the machine and the world that built it. The domestic and the cosmic touch there for a second, and the result is not grandness alone. It is tenderness. Linda Spilker, Voyager project scientist at JPL, said in 2025 that every day could be the mission's last, but any day could also bring another interstellar revelation. That is the emotional truth of Voyager now. We are not watching a fresh launch. We are listening to an old voice that still has a few sentences left, and any one of them could matter more than we expect. What should we look for next? More clues about the plasma density around Voyager 1, more hints from the magnetic field around Voyager 2, more evidence about how far the sun's influence really reaches beyond the heliopause, more chances to compare local, point-by-point readings with the larger maps built by heliophysics missions closer to home. The great unanswered question is no longer whether there is an edge. It is what kind of edge it is, how it changes, and what that teaches us about every star with a bubble of its own. Somewhere ahead, another paper will land. Another graph will show a small bend or rise. Another signal will take nearly a full day to get here. It may be a sign of changing particle density. It may be a fresh hint about the magnetic field. It may be a final, quiet note from an instrument before engineers have to turn one more system off. Whatever it is, the meaning will be larger than the measurement. The next horizon is not a planet rising into view. It is more subtle than that. It is the moment when a machine already beyond the sun's great shield tells us whether the outside becomes cleaner, stranger, calmer, or even more connected to home than we guessed. The dream now is not of spectacle, it is of precision. One old spacecraft, a few surviving instruments, and the patience to understand what its last whispers mean. Save the date, November 18th, 2026, somewhere private, or set a reminder to check where Voyager 1 is then. That one small act gives you a fixed point for measuring how far human curiosity can travel in a single lifetime. When that day arrives, most people will go on with dinner, deadlines, errands, traffic, dishes in the sink, and lights left on in empty rooms. And far beyond all of that, a craft launched in 1977 will slip past the mark of 1 light day from Earth, still carrying the weight of our questions into the dark. I think the future will hold more of these moments than we expect. Not loud endings, not final answers, just faint signals, arriving on time, teaching us that the universe is kinder to the patient than to the certain.